everybody. As promised, let's start off by applying some of the math that we talked about at the end of our class on Monday. What energy is given off by an electron transitioning from n equals 3 to n equals 1? Remember, we talked about Rutherford's planetary model of the atom. These electrons just spin around in orbits. Rutherford said those electrons aren't just in any orbit, and those orbits can't just fall in or go out. They can't just be random. They're specific energy levels. Electrons can occupy specific energy levels, which means jumping from one energy to the other corresponds to an exact equal value of energy given off. First of all, how do we know that this transition is going to give off energy from n equals 3, shell 3, to n equals 1? Good. If it's dropping shells going to a lower orbit, that's always going to give off light. That's the energy emitted. So we just want to calculate E. Remember, we're going to use our equations sheet. We don't have to memorize this equation. We know that the energy of shell 3 is negative k over n squared over 3 squared. The energy of shell 1 is negative k over 1 squared. So we can factor out the 1 over n squareds and the k, and we can get this equation.
Sorry, would you say that again?
The energy of each energy shell is equal to k over n squared, negative k over n squared, and this is k, a constant. That's right. Since we're taking the energy difference between them, then we're going to see k get factored out in front, the negative k get factored out in front, and we just have the difference of 1 over the squares. It's saving you the algebra, if that works for you. Okay. Remember, though, that I recommend, as soon as you get this on the midterm and the final, maybe look for this equation and make a small edit to it. What edit would you make? Yeah. The same way that you always take the difference, which is the final measurement you have minus the initial measurement you had. For instance, if I weigh myself, and then I weigh myself and my cat, I can take final minus initial, and I get the mass of just my cat. Or if I'm timing somebody running, and I would say, okay, they started at 10 seconds, they ran until 50 seconds, final, 50 minus 10, they ran for 40 seconds. This is pretty standard. There's going to be 1 or 2 instances this semester where we don't actually do final minus initial, but most of the time when you're taking a difference, you're doing final minus initial. So E equals negative 2.18 times 10 to the negative 18th joules times 1 over what squared? Good. I'm ending at 1, so 1 squared. Minus 1 over 3 squared. I'm starting at 3. If I were you, I would do this in portions in my calculator. I'm going to solve first for what's inside this parentheses. I think we should know what 1 over 1 squared is. 1. Easy there. So I don't have to plug that into anything. So what I'm actually going to do is do 1 over 3 squared. Oh, I kind of messed up with my buttons. First of all, 1 over 3 squared, larger than 1 or less than 1? Less than 1. We'll limit sig figs here to 3 from our constant, because these are counted numbers. They don't have sig figs. If you're not happy about how that looks, you can do 1 over parentheses 3 squared in parentheses. in case you're scared that your calculator is going to do 1 over 3 squared and maybe give you a different number, you can packet all of these things into parentheses. Gives us the same number. So I've got 1 minus, if you've got this function, you can just click up to that previous calculation and plug it in. Or you can do 1 minus, in parentheses, 1 over 3 squared, which is what we're doing here. We're just putting this in parentheses to make sure that it gives us to us right. I really, really encourage you, get to know your calculator. Plug it in different ways to see if you're getting the same number and that your calculator is not throwing you off. So this gives me 0.888 repeating. I'm just going to abbreviate it at a 9 there, but I'm not actually going to round it. I'm going to use that value in my next calculation. So I take that answer times negative 2.18, and I'm actually going to go back and put all of this in parentheses so that I can do times 10 to the negative 18th without worrying about how the calculator might interpret all of that. The energy here is negative 1.93. I'm limiting myself to 3 sig figs, but this is 1.937. So I'm going to round up to 4. Units? Joules. Good work. Oh, I'm sorry. Times 10 to the negative 18th. I forgot all of those 17 zeros in front of there. It's a very small number, correct? Notice that this says negative. That is energy that is given off. And in fact, I made a mistake, didn't I? This equation is not E. This equation is delta E. Delta means what? Change. And what is the change? It's not positive. The change is negative. Energy is lost. I want to say I maybe misspoke last week, last class, when I said that the lowest energy shells are the ones closest to the orbit. And what I should have said, I'll restate it now, is that those energy shells that have the most negative number are the lowest energy, the closest to the nucleus. And I gave that example of if you're close to the nucleus, you're spinning really fast. But it actually takes more energy to be far from the nucleus and still held on by the nucleus. Maybe counterintuitively, which is why I think I misspoke about that last class.
I thought like if you're trying to pull an electron out, it takes more energy the closer it is to the nucleus.
That's true, because it's a low energy electron. So now to get it out, I have to put in a lot more energy to get it out.
Okay.
I have to put energy in to get it to the third shell. I get energy back when it falls from the third shell.
Okay.
This idea of electrons, I have to put energy in to get to the third shell from the first, and I get energy back when it falls from the third shell to the first, or any shell. This idea that electrons only obey specific energies is very important. First of all, I like this demonstration of what an atom is. Wait for the electron to come around. There he is, just hanging out. There's your atom. That's what Rutherford and Bohr are proposing, and I'm here to tell you they're wrong, but it's funny. I want you to think about what's going to go on with these 3 different masses when he starts shaking the base. Will all 3 of them move regardless of how fast he moves the base, or will only one of them move at specific frequencies of moving it? Have any of you seen videos like this before? Okay, because I see them all the time, so that tells you something about me. Notice how when he goes really fast, just one of those frequency moves. The other 2 relatively stay the same. When he goes really slow, only one of them moves. And then when he finds this medium frequency, the other one moves. The masses only move at a corresponding energy. I've got another demonstration for this too. Similar model, but not 3D printed. Notice how he's going slower, and that long mass is moving. Go a little bit higher, and that intermediate distance is moving. And when he goes really fast, very high frequency, he can get that small one to move. Tell me why this big mass is not moving when he moves it really fast. He's putting energy in. Shouldn't it move? This is the idea I want you to take to electrons. Why is it that I can shoot photons at an atom and electrons don't move, but then I hit a specific frequency with my photon and the electrons do move? This is a physics example, but it correlates to how electrons will transition. Do you want to add to that?
Oh, I was just like noticing that with the other one, they were all different sizes, but around the same length. Whereas this one, they're all
Different lengths.
different, but the center is the same. So.
And in the world of frequency, or in the world of physics, they're all just finding different frequency, resonance frequencies. They'll only move if the frequency matches their resonance frequency. That's basically the same here. An electron will only move if a photon matches the energy gap needed. A photon of more energy doesn't make the electron move. A photon of less energy doesn't make the electron move. This is in your textbook, this image, which is meant to model what I drew out last week. N equals 1, N equals 2, N equals 3, N equals 4. You can go on. But notice the energy levels. There's this huge energy gap between 1 and 2, less than half that size between 2 and 3, less than that between 3 and 4, less than that. Each energy shell gets actually closer and closer to the shell before it. If I provide a photon with this much energy, I can make my electron move from N equals 1 to N equals 2. But if I provide a photon of this much energy, does the electron move? Why? I had more than enough energy. But in that same physics demo, when he was shaking it really fast, he had more than enough energy to make the longest ball move, and it didn't move. It doesn't match the energy level. It's not going to allow the transition. And what word do we give to that? A specific amount of energy required? Quantum. That is a quantized energy gap. It is unchanging, specific, no more, no less. So I want to change this one, and I'm going to put it on its head. What is the wavelength of a photon that is required to move an electron from N equals 1 to N equals 2? I can try. Is this just the same as the last one, or is it different? And I don't mean that it's going opposite, right? This is saying what energy is given off. This is saying what is required to go in. Are you going to use this equation again? Yeah, you will need to, because the energy gap between 1 and 2, you need to know. But do you want units of joules at the end? So this is not the only equation you need to use. What other equation needs to be coupled? Here, C equals lambda V, lambda nu. The energy of a photon is equal to Planck's constant times C over lambda. We'll have to do some algebra to solve for lambda, but we'll get the energy from this equation. So notice that we got the energy here. You could take this energy and plug it in, and you could solve for the frequency of that light or the wavelength of that light. And that's what we're going to do. We're going to solve for the energy gap required and then translate that energy gap into the wavelength of light that matches that energy gap. Okay? Write it out. Why don't you guys try to collaborate? Work with people that are nearby. Write out the two equations that you'll need in order. Solve for the wavelength of light. And collaborate on writing these equations together.
I think that was more focused on the machine, but I honestly anyway, we need to solve okay, so we need to do the and then we use
You guys are going to check each other's work? Great. Lauren, Jackson, you guys want to check each other's when you're done? Feeling stuck on how to start? Start with this. Write out that equation. Delta E equals. And then plug in N1 squared and N2 squared. But you have to decide what numbers N1 or N and which number is N2. Okay?
I wouldn't yet. I wouldn't write it yet. That's not
Set it up right. You're finding this is going to be negative. 1 half minus 1 is good. Okay. So where we got the equation from there. You notice that the equation one or any of the I need an equation that has two different values. If you plug it in specifically,
I was like
to 8. I need that. But you notice the sign of the delta E. Now, we're going to take E or delta E, which is now the energy gap. You're going to plug it into the equation above. Might be smart though to write in the cell variable, do the algorithm.
I started off with the same thing.
Good.
Yeah. I'm sorry, but you plugged in the numbers that
Here, the variable
but then you use
one
the
over
numbers
2
here
here
there to plug into it.
is not 1 half. 1 over 2 squared is 1 quarter.
Which one is it?
Actually, it's more than
I think I got a big number. I don't think that's right. Okay.
Or the one that I don't know if it's that one.
HC is
Did you get a small number? That's probably right. I got 1%. That's probably so. So I brought my already because the rules cancel out and then the seconds just from your
That would make sense.
So we do
I'm just confused.
6.626 times 10 to the negative
try starting on that one.
Oh,
Solve for the energy output. That's the energy. Convert the energy to the photon. What do you think about it?
Okay, and then we know
I think you're multiplying here. Is that what the dot is? There you go.
okay, so I get that, but
That's going to change. Now that you've got 1/4 minus 1, that's a negative number.
that's the
Times a negative number tells us that our energy gap is positive. Good. Yes.
It's just.
I don't know that number exactly, but yes, it does. It does look right. Sure. Although we're not done yet. We need to do another equation. No, E equals HC over lambda. Under C equals lambda V, E equals, skip the middle part, HC over lambda. You're going to have to rewrite it. You're going to have to do the algebra on it. Yeah? And then solve for lambda.
I thought it was just anywhere in the
Oh, it's there. Sorry, I didn't realize.
But
I told you guys to do the algebra.
yeah, we're not great.
I don't know my tool very well, do I? This is the benefit of knowing how to use your tool. If it's there and you don't have to redo the math, don't redo it. All right, so let's talk. We have to do 2 steps. First, find delta E. This corresponds to the energy of the photon needed. That's not really an equation you need to know. I'm just letting you know that the energy gap between the shells is the energy of the electron, or sorry, is the energy of the photon that we'll need. So if you solve for delta E, then you can think of it no longer as change and just as energy needed. Should this number be positive or negative? Do you want to explain why? Shell 2 is higher energy. To get there from shell 1, I need to put energy in. Good. Negative 2.18 times 10 to the negative 18th joules. What is N final? N2. So 1 over 2 squared. What is N initial? 1 over 1 squared. Those squares make a big difference, right? It changes what number you get in that parentheses. Feel free to put it in your calculators if you want to, but this is negative 0.75. The fact that it is negative in there is crucial. If you get a positive number, you have swapped NF and NI. And here's why. Negative times negative, positive, which means the delta E is positive. This, I'm going to reiterate. If your delta E goes against what you have reasoned, we already reasoned that delta E should be positive because I need to put energy in to make this electron get to a higher energy level. If your delta E is negative, you swapped NF and NI. It's as easy as that. And the reason that I don't like calling it N1 squared and N2 squared, it makes it sound like this is where you're starting from, and this is where you're ending. It makes it seem like it's first shell, second shell, but it's not how it should be written. In fact, if this really is n equals 1 and n equals 2, then we're looking at falling from the second shell to the first shell. It's a very specific way to write it. That's why I prefer NF, NI. Okay? Can somebody give me the number they got for that? Negative 18? All right, so I got positive 1.635, and some of you put 1.64. But this is not my final answer, so I don't need to round anything here. And if it went on longer than that, I would just leave it in my calculator. But this is the energy shell gap. That's how much energy my photon needs to have. So now I can plug it in without having to do the algebra. I can just use this equation. 2. Find lambda from energy. Lambda equals Planck's constant, 6.626 times 10 to the negative 34 joules seconds times the speed of light. This is one you'll need to know. It's not on the equation sheet. Who has it? 2.998 times 10 to the positive 8 meters per second. How crucial are units there? So crucial. If you don't have meters per second, it's going to throw off all of the units in your final answer. You could also round this to 3 times 10 to the 8, but it is going to change your final answer by some, so then you would need to recognize if numbers are a little bit higher or a little bit lower, that's the result. Divided by delta E, the energy of my photon, the gap that I need to meet. 1.635 times 10 to the negative 18th joules. First, let's look at units. Joules in the numerator, joules in the denominator, joules cancels. Thank God, because I don't know how to talk about photons with joules in their wavelength. Joules cancels. Seconds times per seconds. Seconds divided by seconds. Seconds times per seconds. They cancel. I'm left with what unit? Great. That's a good unit for communicating wavelength. All right, now we plug everything in. This is a great exercise on your calculator because you've got a lot of different variables you want to do in the right order. So I'm going to actually do layers of parentheses here. I'm going to put multiplication on the top in parentheses and divide by the bottom. And then to keep my exponents well, I'm going to put those in parentheses as well. So 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th. All of those in parentheses. And again, if you feel confident with your calculator and you don't need all those parentheses, good for you. That makes it a lot easier when you're plugging things in. Divided by 1.635 times 10 to the negative 18th. Let's see if you guys got this number. Why don't I have you guys tell me? You got -7?
And
You got -43.
I got -43 on my answer.
I got -24. Maybe I used too many parentheses. Or maybe I didn't put in, oh, well, I put in 1.635 times 10 to the -1. So that's going to change it. If I make that to the -18th, it actually doesn't give it to me in scientific notation. So I count, and by the way, there are ways you can make that change. You can set your phone to always, your phone.
Sorry, it's the same thing.
You can set your calculator to always scientific notation or only scientific notation if it's too big to fit on the screen. I do want to warn you though, if you set it to always in scientific notation, then it will take 1.35 and make it 1.35 times 10 to the 0. And it will make 13.5 1.35 times 10 to the 1. You have to pay attention because it will always have scientific notation. All right, I count 6 zeros, which means I get 1.21, and actually it's going to round, correct? 3 sig figs based on our K value here. 1.218 makes 1.22. 6 zeros means times 10 to the -7, because I need to go past all 6 of those zeros and then one more. Meters. Could we express this without scientific notation? Can we express it with a different unit? Nanometers would be good. Nanometers is times 10 to the -9th meters. Or we could do micrometers times 10 to the -6. What would you guys prefer? It's either going to be a small number of nanometers. No, sorry, it's going to be a big number of nanometers or a small number of micrometers. All right. Let's walk it out so that we can show it. Meters on the bottom, nanometers on the top. Which is my big unit? Meters. I'm going to give it my small number. 1. My small unit, nanometers. I'm going to give it my big number, 10 to the 9th. 1 times 10 to the 9th. You guys agree? 1 billion nanometers in 1 meter. Okay, meters cancels. I'm left with nanometers. All I'm really doing is exponent math. -7 plus 9. When I multiply exponents, I can just add or subtract those numbers. -7 plus 9, +2. So I get 1.22 times 10 to the 2 nanometers, or just move my decimal place to the right twice, 122 nanometers. That's the wavelength required to elevate that electron. Does it track? Does it make sense? You're doing quantum chemistry right now. Are you okay with that? Did you know that in week 5 you'd be doing quantum chemistry? Good for you. All right, I have another question, and it involves this energy diagram that's on the right, more so than it involves the actual orbitals. Let's say, well, actually, I should have given this already. We have some different terms to describe where the electron is. When an electron is at its lowest energy level, we call that the ground state. Lowest possible energy. And that's going to stay with us even when we start adding bigger elements and more electrons. When it's at its lowest possible energy, even if that is not the lowest actual shell. An electron at its lowest energy is at a ground state. What do we call it at an elevated state? Excited. An excited electron means it could be lower in energy. Now here's another interesting thing. Electrons don't have to fall from the highest energy shell all the way back down to the bottom. Electrons can fall within shells. So they could fall from 4 to 2, from 4 to 3, or all the way from 4 to 1. All of these are possible combinations. So I want to have you guys rank some of these. If an electron falls from 4 to 1, if an electron falls from 4 to 2, and if an electron falls from 3 to 1. Which of these emits the shortest wavelength of light? Keon? 4 to 2 emits the shortest wavelength. Let's correlate wavelength with energy. Short wavelength, high energy or low energy? High energy. Gamma rays, very short wavelength. X-rays, UV rays, very short wavelength. Is 4 to 2 a big energy gap? It's what energy gap? It's the smallest out of these options. So, do you stand by that? What one would you say now? 4 to 1. Out of these options, 4 to 1 is the largest energy gap, the highest energy photon, the shortest wavelength. Which of these emits a photon with the smallest frequency? Four to 2. Because frequency correlates to energy how? Frequency and energy directly. Wavelength and energy correlate inversely, which is where we said shortest wavelength, highest energy. Frequency and energy correlate directly. So which of these emits the shortest or the smallest frequency photon? 4 to 2. Because that's the smallest energy gap. Does that make sense? You've got some questions like that on the Module 5. How many of you have done your Module 5 checkpoint already? Good job, guys. Some of you. Good. Did you finish all of your attempts? You're done with it? You're ready to move on? Good. My advice, if you haven't started, don't feel like you need to do all 3 attempts at once. Just take it once. Figure out where your weak spots are. Review those. Go back and retake them. Correct me if I'm wrong, guys, but you don't have to re-solve problems that you got correct. Good. You only have to go back in and finish up the ones that you got wrong. So don't feel like you need to power through and do all of your attempts at once. Take some time between them. But if you haven't done it already, make sure that you get it done tonight, tomorrow. Find a time to do it. All right, any questions here before we move on? Do you think that you'll have to do problems like what we did that involve 2 calculations where you're not told that you have to do 2 calculations? Yes. You will need to figure out what system of equations you need to use. So be thoughtful of that. Take the data you have, What equation helps you solve for something? What are you limited by when you solve that? And then figure out another equation that helps you get to your final answer. It's not always one step. And it's rarely given to you that it's not one step. You have to figure that out. Okay. We're moving into Module 6, which is actually called quantum theory. This is where we get into it a little bit heavier. By the way, I uploaded something to Canvas that I am trying to use to help me stay more on track. I want to say that these are not official documents for the course necessarily, because our course lead has already written learning objectives for this class. You guys may find those learning objectives when you go through the readings. But I find that they're lengthy and they're not highlighted specifically, so there's just a lot of words and I don't know necessarily what is the most useful thing that I'm getting out of it. So I went ahead and made this document, which is listing what skills I hope you can get out of the notes that we take together. These are your learning objectives. I built these using action verbs. So recognize, relate, describe, use. But then I've highlighted those key concepts. Basically vocabulary. If you don't know those vocab, you should go study them. I've uploaded this, which is for Unit 3, Modules 5, 6, and 7, to the very top part of the Unit 3 module. So it's the first thing you can access if you go there. Your book also lists learning objectives. These are not exactly the same, but when I look at my notes, this is what I expect you to be able to do when you're done. Does that sound good? Feel free to use this if it's helpful for you. What we just did was recognize regions and relative energies of the electromagnetic spectrum. Relate the speed of light and Planck's constant with the photon's wavelength, frequency, and energy. Describe line spectra and blackbody radiation. Describe the photoelectric effect. Use the Bohr model to relate the energy of a photon with the difference in quantized electron shells. That's what we've just finished up. And we're moving into quantum theory. Recognize de Broglie's equation, remember the uncertainty principle and Schrodinger's equation, name the 4 quantum numbers, distinguish between valid and invalid sets, and use electron configurations. So that's where we're going. Hopefully, if you've done your pre-reading, you've seen some of those words, and you've got these big question marks that we're going to help erase today. Fingers crossed. Okay. So we learned that light is both a particle and a wave. And this wave-particle duality is not limited to light. All matter is both a wave and a particle. The mechanisms of classical physics didn't work to describe electrons in orbits around heavier atoms. Bohr's model started to collapse, and this is where they realized it's not as simple as an electron moves from here to here. It moves in energy, but they realized they needed to find out different things. This guy, Louis de Broglie, he developed this equation. He found that the wavelength of anything is equal to Planck's constant over mass times frequency. I wrote that as a V, but it should be nu. So remember, H, Planck's constant, given to you on that sheet. M equals mass. nu equals the frequency. So he said things that have mass are actually waves. And then they proved it. They used the double slit experiment. How many of you have seen videos on or have heard about the double slit experiment before? Most of you have not? I don't want to take too much time on this because it's not really one of the heavier learning objectives here. But it can be interesting to look at it. Some of you that go on to physics will do this in a physics lab, I'm sure. You'll take a light source. We know that light is a wave as well as a particle. And if that wave can propagate and hit a barrier that has two slits in it, then two new waves will be created at each of those slits. This should actually be a bit familiar to you if you are familiar with waves in an ocean or waves in a pool. When a wave hits a barrier and only has one opening to go through, a new wave propagates through that opening. But waves are increases and decreases or math equations that go up and down. When you look at a wave in the ocean, you don't say that waves just go up. You always feel that dip of a wave too before it comes up. That's what we describe as constructive and destructive interference. So where these waves push up on each other, you get extra light. And where these waves cancel each other out, one goes up while one goes down, so they actually don't exist there, you get these regions of darkness. This is light. Light obeys the double slit experiment as we expect because we think of light. We think of light as a wave very often. But if you do this with electrons, you get the same results. Shoot electrons at a screen that has two slits, and you get this pattern, this interference pattern. So it's hard to draw. I'm not going to bother drawing it. I'm just going to say the double slit experiment gave us electron interference patterns. And it's quite interesting. If you shoot one electron, you don't get this pattern. If you shoot one electron, it either goes through one slit or it goes through the other, and then it hits the backdrop. And then you shoot a second one. It goes through one or the other. It's not until you've shot hundreds or thousands of electrons that you actually see the pattern start to arise. But the only way the pattern can arise is if that electron is behaving as a wave, regardless of if it's in the presence of other electrons or not. It is a very strange thing. This is the part of quantum mechanics where if your head hurts, you're doing it right. And that's okay. Get comfortable in that uncomfortable spot of seeing how it doesn't obey anything about classical physics. So they proved it. They proved that matter is both a particle and a wave. And this is where we actually get into quantum mechanics. How does it all work? Any of you guys know a mechanic? Yeah? Well, you all know me. My dad owns a mechanic shop back home. I grew up as a mechanic. What do mechanics do? They fix stuff, sometimes. They make your car work. That's true. That's mostly the oil. Come to my organic class, we can talk about oil. Mechanics know the mechanisms of your car. So when you've got that rattle, your mechanic is the one that says, oh, well, this is not working right. We're going to have to go in and fix this. That's what we're talking about when we say quantum mechanics. We're saying, how is it that all of this all of this stuff works. And I apologize, I didn't want that to be an arrow, but more of a header. This guy named Heisenberg was pretty influential in quantum mechanics. Any of you know Heisenberg? The blimp was Hindenburg, but it's very close. Maybe, yeah. I don't know. Heisenberg sounds German. But I think of Breaking Bad, where that was his calling card, was Heisenberg. Heisenberg found that you cannot know two things about an electron. He found this equation. Change in x, which is change in position, times the mass times the change in velocity is greater than or equal to Planck's constant over 4 pi, whatever that means. According to this equation, and I will say it's beyond the scope of this class to prove how this equation says it. According to this equation, you cannot know both the velocity and the position. Of an electron, that's correct. You cannot know both position and velocity. Position represented by x, velocity represented here by delta v. So the old saying goes, Heisenberg got pulled over on the highway, and the police officer came up and said, "Sir, did you know you were going 70 in a 55? And Heisenberg says, "Great, now I have no idea where I am." Can't know both the velocity and the position. You can either figure out where it is, but you have no idea how fast it's moving, or you can know how fast it's moving, but you don't know where it is. That's quantum mechanics. That's our uncertainty in quantum mechanics. It's cool stuff. This is what separates quantum physics from classical physics, is that classical, you know where it is and how fast it's moving. Quantum, you know one or the other. Schrodinger came along then. And you know Schrodinger's pet? Schrodinger's got his pet cat. He gave this equation. Schrodinger says h hat times psi is equal to the energy times psi. Oh, that's like such a nice math equation. Easy. I'm not going to get into it. H hat is just a lot of math, like a lot of math. Psi, this is a Greek letter, but it looks like Poseidon's trident. This is the wave function. You know what a function is? Something you turn up to. No, just kidding. It's a math equation, right? A function is just a math equation. So this is actually the math of the wave. The wave of what? The electrons predominantly, but you could scale this and talk about protons or nuclei or you. You have a wave function. E is the total energy. So Schrodinger was the one that said, we can actually develop this. We can calculate something about the electron. We can get a math equation that describes the electron. And here's what one of those equations looks like. that is a sphere. It's an equation that describes a sphere. Do you guys know how to write an equation that describes a sphere? I don't really. It's probably got pi in it somewhere. Do you know someone who could write an equation to describe a sphere? If you've ever had a math teacher or a math professor, you probably know someone who could write an equation to describe a sphere. But there are some weird things about psi, the wave function, and I'm gonna talk about it a little bit more. But here's another equation for psi, not a sphere, and it's got two colors. Those colors mean different things in the math equation. It means that in this part of the function, the math equation begins with plus. And in this side of the math equation, it begins with minus. This may be a very bad simplification, but it does describe different things. For instance, if I wanted to describe your car moving, if it's moving forward, I want to describe it with plus. And if it's moving backwards, I want to describe it differently with minus. This is describing how the electron behaves, where it is, what orientation the electron has in space, and how it's moving. But because we're describing a math function, we use colors to differentiate what the math function is doing.
You just said that basically we know the position and like how it's moving, but I thought the whole thing is you can't know both.
You can't know its position and its velocity, but we can describe an equation that says this is where it is, and I'm going to explain this in a bit. This is where it is most of the time, and it behaves differently in these two regions.
So it's not exact.
That's right. Here's another, and so I want to point out, sphere by itself. These we can call propellers, or you can call them petals. The way that I draw them is not quite as rounded and lobed. The way that a lot of people draw them is a little bit more oblong. So you'll see why we call them petals. And then up here is another set of equations. More complicated, right? Most of them are very similar. You've got these 4 eggs, and you're just orienting those 4 eggs in different ways along the x, y, and z axes. That is important. How those eggs lie along the different axes changes their orientation, makes them unique from each other, makes them unique ways to describe how an electron exists and behaves. And then you've got this guy in the middle, 2 balloons reflecting over a donut. This is the dz squared orbital. It's one of my favorite ones to draw. All of these sets of math equations have some things in common. 4 lobes. Actually, 2 nodes is what we say. There is this region that cuts this way, where electrons are never found, and a region that cuts this way, where electrons are never found. A region this way and a region this way. A region this way and a region this way. This way and this way. All of these orbitals have 2 lines that separate where electrons can be found. This one is the strangest one because its 2 lines look like this. But it's still 2 lines that separate where these electrons can be found. That's what all of those shapes have in common. They are different versions of basically the same math equation, the same wave function. Actually, I should say they're different solutions to the wave function. These shapes solve for the wave function. By the way, you're not going to have to recognize these shapes very much, not the D ones at all until you get into probably inorganic chemistry. These we call P. What do you notice that all 3 of these have in common? 2 lobes, which means how many nodes? I'll describe that word in a minute. 1 node. There's this one region where electrons are never found. Here's that region here. Here's that region here. Just 1 node. differentiates from that. These are the only three solutions to the wave function where you have one node. And then how many nodes here? None. That's why you don't get these two lobes of the wave function. You just get one lobe because electrons are found everywhere. Okay, so some terms that I want you to write down before I give you this break. We call these orbitals. Orbitals are a solution to the wave function, psi. I'm going to reiterate this. Orbitals are math equations. Orbitals describe size, shape, orientation. Is it along X? Is it along Y? Is it along Z? How is it oriented in space? And the shading gives us plus or minus on the equation. Just describes behavior. That's how I want you to think of it. If you think of it that way, then it will make the most sense, in my opinion. All right, and then lastly, the nodes where electrons are never found. Electrons are never found here, despite this being one solution. Can an electron that's found here ever end up over here? Why? Because it can't go through that region? This is the electron, but it's never found here. Guess what? If you want to go from here, class, to home, you have to go all the way through that physical space separating you from home. Electrons don't have to. Electrons are here and here without being here. It's not even so much that they need to move from here to here. Electrons are here. Okay, but think of it this way. What if I have a wave in a pool that looks like this? You would agree that this is a wave, and you would agree that this is a wave, but actually, if you looked right here, that's not a wave, that's neutral. So how is it that the wave is here and here, but is not here? Electrons are waves. This describes what they look like. Cool. Very cool. And what I was saying with shading, plus, minus. That's what it's trying to get us to. Let's take a 5-minute break. Even if you don't want to leave, why don't you get up, stretch your legs, get your blood flowing again. No, go ahead. Okay, biggest is not quite enough. Longest wavelength or highest frequency, biggest frequency. That changes it.
Okay. And then the longest has the least amount of energy?
Longest wavelength is the lowest energy photon
Yeah, because the
and has
red
the
is super big.
smallest frequency.
Okay, I get that, but when you were asking the questions of like 42 and 3 to 1, it went right over.
Well, I asked two different things. I said, which of these transitions, an electron that falls from 4 to 1, an electron that falls from 4 to 2, or an electron that falls from 3 to 1, which of these transitions releases an electron with the longest wavelength? That's still not enough. Longest isn't enough. You have to put lambda wavelength.
Okay, well this one
Put lambda. There you go.
has the,
Oh, it's okay. It's basically just a y.
okay,
But you can
Okay.
do it fancy.
okay.
Yeah.
Some of the Greek symbols, I'm like,
Poseidon's.
I literally wrote like tried in my notes like try it.
Which of these is the longest wavelength? Longest wavelength is the smallest energy.
Yeah.
That's going to
This is-
correlate to the smallest energy gap. 4 to 2 is a very small energy gap.
Yeah.
3 to 1 is big. 4 to 1 is even bigger.
Huge, but wouldn't it have really low energy, but it's longer?
Longer what? No, the smaller the energy of the photon, the weaker the photon, if you will.
Yeah.
The longer its wavelength. Radio waves
They're
have wavelengths that are on the order of
Rolling
buildings to
hills,
blocks.
yeah.
Yes. They can literally get into the mountains and then they get blocked at some point.
Yeah.
That's a very low energy photon.
Yes.
That's a very long wavelength.
Yes.
That's a very small frequency. Low energy, small frequency, long wavelength.
Long wave, low frequency.
Good.
Okay.
Low energy, small energy.
Small energy. That I get. I think.
Then I asked another one, and I said, take care, Ellie. I said, which of these has the shortest frequency, the smallest? Is that what I said?
Well, this one has a really low frequency, so
I said
when
the
it
largest
started,
frequency.
The largest frequency? Well, yeah, that one I can tell you it's that one because it's the whoop whoops. Oh my gosh.
Frequency correlates how to energy?
They're not the same, but they're
Proportional.
yeah.
Directly related. So largest frequency,
Is gonna have large energy.
largest energy. Largest energy actually has the shortest wavelength.
Yeah, I can visualize that. Like that makes sense to me because it's like the versus the.
Okay?
I'm making
That's
so
that.
much sense. Oh my gosh.
That's
Sorry.
that's the same.
Okay, but I still don't. When it comes to the questions, it like just fries my brain somehow.
Then try to pull out the information from the question. It was hard because I verbally said the question.
I'm definitely nodded.
You're going to have written examples. So you pull out information from the question and say, it's asking wavelength. Convert that into lambda.
Okay.
And then next to it say lambda frequency when this is
Isn't
long,
lambda
this
just
is small.
wavelength?
Yes.
Okay, but then when I was saying it's short wavelength, you're like, it's
Short wavelength,
I don't
high
know.
frequency.
Okay.
They're inverses of each other.
Yeah.
As wavelength increases, frequency decreases. As wavelength decreases, frequency increases.
Okay. So what was the second question again?
Second question, I forget exactly how I said it, but it was which of these has the highest frequency light emitted?
Okay, that would be 42. No?
4 to 2 is the smallest energy gap. That's the smallest frequency light. Small energy, small frequency. Notice how these two things are proportional to each other? When lambda decreases, frequency and energy increase. When lambda increases, frequency and energy decrease.
I thought from 4 to 2 it was the really small, close together.
Their energy gaps are close together. So the energy difference between them is very small.
And low.
4 to 1 is a very big energy gap.
Low energy would mean long wave, and low. I think I'm just gonna have to memorize the correlation because intuitively that doesn't make sense to me.
Yeah, I mean that's okay. That's okay if it doesn't. Maybe if you see some examples too.
I am definitely yeah, and see, I would think that this is 4 to 2 and this is 4 to 1.
You shouldn't.
Yeah,
This is, which of these is higher energy?
the second
Why?
one. 'Cause
Right?
yeah,
And this one is,
yeah.
this is high energy. So 4 to 1, big energy gap.
See, that's where it's like I can tell you.
You think
that-
4 to 1 is not a big energy gap?
No, 4 to 1 is huge, but it feels like a long distance, so it needs the long wavelength.
Okay, don't think about it being this versus this. That's not
That's
correct.
what I'm thinking.
Okay, get that out of your mind.
How?
Well, you've got to work on it. Look at it this way. I'm not drawing waves between these. I'm drawing energy. Energy, not wave.
Okay, and yeah, that's
How do these energies compare?
one is okay.
Small energy, big energy. Big energy,
Yeah, it's gonna have
small
to-
energy.
Okay, that makes a lot more sense because I was totally thinking of it like distance, and I'm like,
There you go.
this one, this.
It's good to catch that. Not throw it away. If you don't catch it, you can't throw it away.
Well, I could tell you like I'm thinking of it like distance, so I'm anyway.
Then you just gotta lean into what helps.
Were you saying that, like in the beginning of the semester, like there's going to be an assignment that was optional after the first two? Was that,
Discussions,
was it discussions that were
Yeah.
optional?
which it's not even optional. Like you're not graded on it at all.
Okay.
They're just there if you guys want to post things.
And then the AI one, is that also?
AI you have to do,
Okay.
but the explorations are also optional.
Okay.
They're always optional though, but you get bonus points for those.
Okay.
The discussions, there's no bonus points,
Alright.
just a spot.
All right, thank you.
All right, I want to clarify. This is not going to change how you get graded on these topics, but there is actually a difference between psi and psi squared. Psi squared is psi is the wave function, but psi squared is the probability density.
Just how likely an electron is to be emitted.
At any given spot, how likely is it that you find your electron? So I said the orbitals are solutions to psi. That's a bit of a stretch, actually. The solution, or the orbitals, come more from psi squared, this probability density. And we actually cap them. We cap orbitals at 95% the probability density. The reason we do that is because the probability is non-zero that any electron in this room right now may be on the moon. Did we talk about this on the first day of class? I might have talked about it with my other classes then. I often talk about this when I talk about the 4 fundamental forces. Electrons are weird. You have a non-zero probability somewhere within that psi squared that one or all of your electrons are on the moon at any given instance. But there's a 95% probability that they make up these nice, concise shapes. So what's going on with that other 5% is that it trails off towards zero for infinity, but it never really gets to zero. So we're looking at most of where the electron is. 95% of the probability of where the electron would be found. And that, again, is the size of that area that the electron is found in, the shape of that area, the orientation of that area. All of those things are included. Does that make sense? I'm sorry, I want to take attendance before I forget to do it at the end of the day. So we're going to look at what we call some of these. But just for clarity, for hydrogen, at its lowest energy, we get this spherical orbital. So remember, Bohr said, oh, the hydrogen is in orbit. Orbitals are not orbits. They are three-dimensional shapes. That electron is not at a specific distance from the nucleus. It's just at a specific energy somewhere inside of this sphere. And if you were to sketch out what that math looks like for psi squared, you get something that looks like this. We're taking a cross section and saying, how close to the nucleus will that electron be found? You'll notice that the electron won't be found at the nucleus. It goes to 0, so it's kind of got this pocket inside of it that you can't see. Because if the electron does go to the nucleus, the proton and the electron collide and neither of them exists anymore. They become a neutron, which is not good. If you excite that electron to the next energy level, you actually get another sphere that has this bigger sphere outside of it, and the two spheres have different colors. And there's a node in between. There's this region where the electron goes from having one behavior to a different behavior, plus to a minus, according to the wave function. This is the lowest energy shell. This is the second lowest energy shell, the next highest energy. This is N1, theoretically, and N2, but it's not just these orbits, it's these big 3D shapes.
So like the smallest one is inside and then there's the outer shell. Does that mean that the node is a circle on the oh my gosh, in between the two? Because I thought the nodes were like planes.
It looks like this. It's a spherical plane.
Okay.
If you can call it that. It's a spherical node. That's correct. Actually, we can say that. Spherical node. This is what it looks like, where this is the shaded part on the inside, and this is the unshaded part. I want you to pay attention to this. The higher energy electron orbital shares some of the same space. Electrons of different energy can be at the same place relative to a nucleus. But when they are there, they have different energies. So it's kind of like how you can be walking at Liberty Park and someone else can be running. You're at different energy levels, but you're occupying the same space. But notice that in the second highest energy level, it spends most of its time further away, but it does spend some of its time close nearby. Then we can excite it another time. Here, we get a third node. First, shaded. Second, unshaded. Third, shaded again. And does that get confusing? Yeah, you bet. There's a node right here, and there's a node in here. From shaded to unshaded, from unshaded to shaded. And this looks like a little dip here, a dip here, and a bigger dip here. And by dip, I mean opposite of a dip. Shaded, unshaded, shaded. Just describing some character of that electron. Does it move this way or that way? How is it behaving a little bit? It changes behavior at each of these levels. Again, at this third energy level, you're most likely to find the electron further from the nucleus, but there's some chance that it overlaps with the second and the first. Instead of calling these n equals 1 and n equals 2, we start to name the orbitals by their shape. These spherical orbitals are called s orbitals. So we call this 1s, 2s, and 3s. Is this as cool to you guys as it is to me that these electrons follow math equations that look like these shapes? It can be a lot to wrap your head around sometimes, but it is wild that we can predict this kind of stuff. They did a lot of just sitting around talking. Schrodinger's equation gives us 3 quantum numbers. These quantum numbers describe properties of the orbital. They describe the energy level of the orbital, the shape of the orbital, and its orientation in space. Those things that I was talking about. The energy level is basically describing its size. So here they are. First, we get the principal quantum number. This is given the symbol n. This describes the energy shell and roughly the size of the orbital of the electron. Where will you find the electron? How do you find the electron behaving? N is always a positive number. I should actually clarify. It's a positive number. Oh, I guess 0 is not a positive number, is it? I don't have to clarify that it's greater than 0. But that would be true. It's always greater than 0. 0 is not positive, is it? It's not negative either. Just chilling. That's where we're looking at here. N equals 1, n equals 2, n equals 3. We're describing the energy shell, the principal quantum number. The second number that Schrodinger's equation gives us is the angular momentum. We give this the symbol L. And I do want to point out, I'm doing my cursive L so that you don't mistake it with 1 or capital I. I encourage you to do the same because there will be a lot of 1s when we talk about quantum numbers, and it can be nice to represent L a little bit differently. The restrictions on L. This is an integer from negative n to positive n. I'm so sorry. That's the next one. Oh, how embarrassing. Erase that. This is from 0 to n minus 1. It felt really wrong when I was saying it. Put it down wrong. L must be a number from 0 to positive 1. L equals 0 means that we have no angular momentum. And that's actually spherical, which feels weird because you probably are thinking of angular momentum as being swung around. But things that are just spherical have no angular momentum. These things that have different lobes, those have angular momentum, different levels of angular momentum. This has one level, L equals 1, and this has 2 levels. We're going to come back and name those more.
Just like the nodes.
Yeah, the nodes, actually we can say that. These equal not spherical nodes, but angular nodes. As opposed to what we saw with 2s and 3s, which were spherical. These are angular, the ones that are planes that we showed before. The third and final quantum number that Schrodinger gives us is the magnetic quantum number. I'm going to abbreviate quantum number there as Qn. I forgot to put quantum number at angular momentum. I don't think it's really going to change your understanding, to be honest, if you don't have it. But it's the quantum number that describes the angular momentum. We give this the letter m sub L. I like this because m kind of corresponds to magnetic. L tells you that m sub L, the magnetic quantum number, is dependent on L. These are the restrictions. This is an integer, and this is where I messed up before. This is an integer from negative L to positive L. The way that you can think about this is that it assigns orientation in space. These 3 orbitals all have the same n. These 3 orbitals all have the same L. How can you tell them apart? Their orientation in space. This lies along the x-axis, this the z, and this, or excuse me, yeah, x, z, and y. This type of orbital has L equals 1. It has 1 angular momentum. Its quantum number for angular momentum is 1. It has 1 node. This can be described as negative 1. This can be described as 0. This can be described as positive 1. It's describing orientation in space. This can be negative 2 because there are 2 nodes. Negative 1, 0, positive 1, and positive 2. This is the application. This is where they're coming from. There's one equation that doesn't come from it. The fourth quantum number doesn't come from Schrodinger. It came from experimental things. This is the spin quantum number, and we call this m sub s. I do still want you to think about magnet when you see m. This is the magnetic spin number, essentially. Do you remember on the first day that I told you electrons, charged particles, spin, creating magnetic fields? Because when charged particles move, they make magnetic fields. This is why electrons pair with each other. Because one magnet spinning one way wants to align a magnetic field with a second magnet spinning a different way. So we say electrons spinning this way versus electrons spinning this way. They get different magnetic fields, north to south, that interact. So we describe m sub s as half integers, positive 1/2 or negative 1/2. That's it. Those are the only two options. And you can think of this as spin up and spin down. When the magnetic field points one way, when the magnetic field points a different way.
So like with their spin fitting, having different electromagnetic fields, does that mean like they are somewhat attracted to each other, these electrons?
Yeah. We should think they repel because they are like charges. And electromagnetism says like charges repel.
So is it wrong to say that electrons repel each other? Or
No, it's not. It's actually a little bit better to say that pairs of electrons repel other electrons. Once electrons pair, they are stable. But they're not stable until they pair. If you have one electron that's unpaired, we call it a radical. And just like the colloquial use of the word radical, those electrons are highly reactive, prone to do anything to get a pair. Yeah?
interesting stuff.
Thank you, Cole. A+. So, electrons repel each other, except for if they spin opposite ways, then they attract each other. And so, two electrons will always exist in any given orbital of a shell, of a subtype, and of an orientation. Two electrons, one spin up, one spin down. So we get 2 electrons per orbital. Per orbital of n, l, and m sub l. All right, now I want to actually dive into these just a little bit more. First, we'll talk about n, and it's actually somewhat easy to talk about n and look at the periodic table. So if you have a periodic table, pull it out. I might pull ours up too in a minute so that we can talk about this. I don't think I'll keep this on for too long because it gets in the way of me using this board, but I will point this out. This roughly correlates with the periodic table. Here's our first energy shell. N equals 1. N equals 1 only contains hydrogen and helium. Those, I should say this, hydrogen and helium are the only atoms whose electrons are only in the first energy shell. Once you get atoms in the second row, they have electrons that fill the first energy shell, but now they start to fill the second energy shell as well. Then you get electrons that fill the third energy shell. And this is where it gets more complicated, and we'll come back to it. This begins the fourth energy shell, but this rectangle that I gave you here, the transition metals, these are actually back into the third shell before they go back into the fourth shell. And then the fifth, but the fourth, and the fifth. And then the sixth, but the fifth. I said something wrong. What was this? 1, 2, 3, 4, 5, 6. Then the fourth, then the fifth, then the sixth. roughly correlates with the periodic table. If you're tracking on the right-hand side or the left-hand side, we call these the main group elements. Then their energy shells directly correlate with the row that they're in. But for the transition metals and the inner transition metals, it's not quite as simple. We'll talk about why. Okay? That's N. An electron with larger N. You guys okay with my abbreviations? Sometimes they can be a little annoying because they're not sounding out everything. But I'm trying to use shortcuts to help make it feel a little bit more visual and less wordy. Electrons with larger N have higher probability further from the nucleus. We talked about that. N equals 3, those electrons are probably the furthest from the nucleus, although they have some non-zero probability of being closer to the nucleus as well. Every electron has to be in some energy shell. And we represent the energy shell that electron is in with N. L. Divides N by the shape of orbitals. We call these subshells. They are sets of orbitals that all have the same shape within a shell, subshell. You might think of this as a shelf at a grocery store that is all on the same height, but divided into cleaning products, food, and clothing. That was a weird example, right? But different things that are being held on the same shelf, subshells. What happens if N equals 1? Our smallest energy shell. When N equals 1, L equals 1 minus 1. I'm sorry. And when N equals 1, L equals 0. L equals 0 is what we call the s orbital. L equals 0 means that it has no angular momentum. It has 0 angular nodes. It's just a sphere, although sometimes it's a sphere with a sphere inside of it.
I thought when it has a sphere inside it, doesn't it have
A spherical node, not an angular node.
Oh, okay, you're right.
If N equals 2, what am I allowed? And 0. L equals 0 or L equals 1. At the second energy shell, 2 orbitals are created. L equals 0 now has an s orbital with a spherical node. L equals 1 is what we call a p orbital. I should draw these so that you guys can see. S orbital, sphere, p orbital, 2 lobes, 1 shaded, 1 unshaded. How many nodes does L equals 0 have in N equals 2? 1. How many nodes does L equal 1 and N equal 2 have? 1. But they're different types of nodes. N equals 2, L equals 0 has a spherical node, just 1. N equals 2, L equals 1 also has 1 node, but it's angular instead of being spherical. When I get to n equals 3, what is L allowed to be? 0, 1, and 2. When L equals 0 here, what type of orbital is it? S. It's an s orbital, spherical orbital. How many spherical nodes does it have? It's always L equals 0, which means it never has an angular node. But now it has 2 spherical nodes. That's what we drew before. We drew 3s, and we had 2 nodes, 3 balls inside of each other. What about L equals 1 at this level? What type of orbital is it? This is a p orbital because it's L equals 1. That's the definition of p orbitals. How many nodes does this p orbital have? I'll give you a hint. It's the total same number of nodes for all sets inside of an energy shell. With 1 spherical node. I don't need to say that it has 1 angular node. L equals 1 already says that. But now it gets a spherical node. And this, honestly, don't worry about trying to draw this if you don't want to. This looks really goofy, but it looks like this. It's one big propeller surrounding a little propeller. And you go from shaded to unshaded, and unshaded to shaded. Here's the sphere, where the orbital changes phase, where it changes from plus to minus, just like it did with S. It gets way too complicated. You're not going to have to draw it or understand it. But this is what's going on inside of it. P orbital goes up another level. It gets a new type of node, a spherical node. Just like why S got another node every time it went up. Same number of total nodes, different way that they're solved. L equals 2. This is called a d orbital. Those d orbitals were the ones that you were looking at. Most of them look like this flower, but they're oriented different ways along the x, y, z axes and planes. And then there's one that looks like this. But you're not going to have to be very familiar with these shapes until you get into higher level inorganic chemistry. But I do think it's fun. How many nodes here? 2, 2, 2. All of the orbitals inside of a shell have the same number of nodes. But they take nodes in different ways to be unique solutions to the wave function. Right? All right, n equals 4. L can equal 0. L can equal. L can equal. L can equal. Good. Now I think you get the idea here. S, P, D, 3 spherical nodes, 2 spherical nodes, 1 spherical node. This is what we call the F orbital. And I'm not even going to attempt to draw the F orbital because it's too hard. But how many nodes does it have? You say 0. 3. It has 3 nodes. They're all angular.
Like a snowflake.
It does actually look a bit like a snowflake. It gets some. It's got like 6 lobes. The D has 4. The F has 6. Now these also correlate with the periodic table. So I want to remind you that when I showed you the periodic table the other day, last week, we actually talked about some names that they have, parts of the periodic table. If you have your periodic table, this might be useful to point out. Group 1 and Group 2 is called the S block. These atoms have their highest energy electrons in an S orbital, which is why we call it the S block. Their highest energy orbital is S. How many electrons can fit in an S orbital? 2, which is why the S block is 2 columns wide. I can fit, an S orbital is just sphere, so I can fit 1 or 2. Then I get the P block. That P block is this square that you have on the right-hand side. By the way, helium belongs in the S block. But it's very familiar with its properties to the noble gases. Hydrogen and helium are those oddballs. This is your P block. The highest energy electrons here are in P orbitals. What do we call this? The D block, where the highest energy electrons are in D orbitals. And what do we call this? The F block, where the highest energy electrons are in F orbitals. There is some very fun stuff that happens when you start trying to fill electrons between D and F. And luckily, it's not a big part of this class, so cheers to you. One fun thing, do you notice how 2 atoms are actually missing from the D block, and they're drawn in the F block? That's because there are no 2 atoms in this group that behave most like the other D elements. They're all kind of misfits relative to the rest of the D block. A little strange. I had some problems with my professors in undergrad about that. All right, so that's L. The S subshell, the P subshell, the D subshell, the F subshell. By the way, we don't have elements on the periodic table that have them, but after F, you just keep going up. G, H, I, J, K. And they're all theoretical math solutions, so they all work. And then we get M sub L. M sub L defines which of the specific orbitals you will find your electron in. With each increasing subshell, you get an increasing number of orbitals. S subshell always has 1 orbital. P subshell always has 2, 4, 6, 3 orbitals. D subshells always have 5 orbitals. F subshells always have 7. 1, 3, 5, 7. Each subshell gets an increasing number of orbitals.
And in like the electron clustering, right? Like the orbitals, they're all centered together, right? Like it's not like, oh, the D's over here and the F orbital's over here. They're like,
Yeah, they all take up the same amount of space relative to the nucleus.
okay.
So you're just kind of lucky that they never run into each other. Or maybe they do, but they're very
They
small.
are like next to each other, not necessarily overlapped.
Correct. That map that I drew, they were overlapped with each other, but just smaller and smaller probabilities with higher and higher orbitals. So I want to give an example. If I have n equals 0, if I have n equals 1, what can L be? Only 0. L is from 0 to n minus 1. Well, n minus 1 here is 0, so I only have 0. What can M sub L be? M sub L ranges from negative L to positive L. 0. There is one orbital of S per S subshell. Now let's go up a level. Let's say n equals 2, L equals 0, M sub L is 0. There's only one orbital it's in. But L equals 1, the P subshell, M sub L has 3 solutions. Good. -1, 0, +1. Which tells you which of the 3 orientations your electron has. How many electrons can fit in this M sub L orbital that equals 0? 2. How many can fit in N sub L equals -1? 2. M sub L equals 0? 2. M sub L equals 1? 2. This is why the P subshell can hold up to 6 electrons, 3 orbitals in each. 1, 2, 3, 4, 5, 6. It correlates with the periodic table. All right, I've taken you guys over. Thank you for your time. When we come back next week, we're going to finish up talking about electron configurations and talk about periodic properties that these electrons give us. Have a good weekend. Feel free to get a head start on Module 6. Checkpoint.
Thank you.